Mic check. Hello.
Okay, so I guess yeah, at most we'll just wait for 2 more minutes on that. Is that okay? You're already live, okay, Mandar? I should keep the mask on, right? No?
It's here on, but while speaking, I prefer you.
Sure. Yeah, I don't see what Sure. Okay, well, I think it's 4 o'clock and we're going to start now. So it's a pleasure to welcome everyone back to the NSF. And today we have one of our own experts within the TIFR community giving today's colloquium. It's Professor Mandar Deshmukh from the Department of Fundamental Physics and Material Sciences, who's going to talk about topology and quantum geometry, including moiré materials. Before Mandar actually goes into his talk, I would like to mention that the NSF Wednesday colloquium has been an age-old tradition for all of us. It has been sort of a very pioneering vision of Professor Mumbai, the founding director, that allowed for all of us to get together every Wednesday at 4 and listen to any of the experts within the subcommittee of physics, chemistry, and biology to sort of give a colloquium on topics of relevant interest within the subcommunities, and as well as allowing people to cross-talk within the institute on these very interesting research work. So today is no different. Professor Mandar Deshmukh has been with us in TIFR for almost now 16 years, and he has been leading a world-class research group from TIFR, specializing in sort of discovering new physics phenomena at the nanoscale, as well as integrating these ideas of physics to develop nanoelectronic devices. So, Mandar, without further ado, we are awaiting your colloquium on 2D materials.
Okay. Can you hear me? Yeah. Okay. Thank you very much, Deshmukh, for having me here for the colloquium. It's a pleasure. Is this one? Okay. Okay, sorry. Good one. All right, so it's great to be here. So today I'm going to talk about some of our recent experiments that we have been doing over the last couple of years through the pandemic, looking at physics of moiré materials. So I will explain a little bit more in detail, but I won't throughout the colloquium not make it very technical. Moiré materials are a class of materials formed by placing two-dimensional materials at a relative twist angle with respect to each other. So, you should think of moiré if you are looking through a mesh in your window and you put another mesh relative to it, you get another beating pattern. That's sort of the etymology for the word moiré. So these are a new kind of materials that are possible by arbitrary twist angles between two-dimensional materials. They lead to some interesting physics in ways that has not been explored in condensed matter physics at all. So they really can shed some new light. So that's sort of my sort of one or a couple of sentences introduction. And to this topic that I'll talk about, so I'll connect these two words, this idea of topology and quantum geometry, These systems allow exploration of these ideas and testing some of the ideas. And this is a fast-growing and very young field. So before I start, I gratefully acknowledge the funding that we get for our work from the Department of Atomic Energy through TIFR and must have stopped. Now you should be.
Could you do, yeah, full screen is fine, yes.
We gratefully acknowledge the funding that we get for our work from Department of Atomic Energy and Department of Science and Technology. So I also want to, at the outset, acknowledge the people who did the work. I'm very grateful to have some very motivated group members and who worked through all sorts of difficulties throughout the pandemic to make some of this work happen. People who led this work, Pratap, student, and Subhajit, who are also senior PhD students. My postdoc, Varma, contributed by coming up with some very interesting way to fabricate these devices, and some JRF who contribute to some part of the work. My collaborators for this work is Amit Agrawal's group at IIT Kanpur, Umesh Wagmare from JLC and student, and some older work that I'll present, which is collaboration with Jail's group at the University of Seoul, and Bhima, who was there as a postdoc now as a faculty at IISc Kolkata. And some older work which actually got us started in this field of twisted devices was with Rajdeep and his student Umesh. And we get some really very important material, which is hexagonal boron nitride. I'll try to emphasize from Dr. Watanabe and Taniguchi in NIMS Tsukuba. Okay, so we get very able support from our scientific staff for all these experiments, Digambar and Santosh. All right, so just a quick sort of idea about what we do. So we work on lots of different aspects of two-dimensional systems, focused on looking at electronic properties. We look at twistronics and quantum transport, look at nanomechanics, mechanics of materials which are only one atom thick or a few atom thick. We have in the last 4 or 5 years started looking at magnetism of their materials, then superconductivity, particularly high temperature superconductor, down to 1 unit cell limit. I talked about this work about roughly 2 years back in the colloquium. And then also a significant amount of our effort is in looking at Josephson junctions as a platform for doing making interesting quantum devices. But today I will focus on this particular sub-area that we work in, which is just the field is called twistronics, which is essentially twisting layered materials and studying their electrical transport at very low temperatures, high magnetic fields. Okay, so let me get started. I will quickly show you the outline of my talk. I will show this at different stages of the talk just to tell you where I am going. So I'll start with a fairly pedagogical introduction to physics of, which is broadly known as Berry physics and topology as understood in the context of matter systems. What's interesting and exciting. Then I'll talk about what is this idea of twisted materials or twistronics, and how it allows engineering materials in a way that has never been done in matter physics. Then I'll talk a little bit in detail more towards the second half of my talk about our actual experiments, which look at the physics of Berry curvature and physics of topological transitions in these layered systems. If I have time, I will also talk about a very interesting system where we see magnetoelectric coupling in something which is comes out of this layered twisted material. Okay, let me get started. So in solid state physics, we often have lots of approximations that we have free electron, and that has some limits in terms of what kind of physics it can explain. If you want to talk about semiconductors or band gaps in the system, one has to certainly move away from that simplified approximation of free electron, and you say, no, there is this periodic potential which the ions in the whatever the symmetry of the crystal is will imprint, and the electrons see that corrugation in the potential as they move around. And to understand their properties, one uses this approach that electronic states are not continuous, but they have intervals of energy where there are states and then there are gaps. So, for example, I sketch here sort of the simplest scenario of a band which has a set of electronic states. Y-axis is energy. So these are set of electronic states where electrons can actually go and sit. X-axis is momentum. Now there is a band of energies which is where there are no electronic states, so there are basically no electrons which can go and sit at those energies. And then as you fill them up to a higher energy, you can again start filling more electrons. So this sort of one other way to think about it is if I plot the density of states, which is basically telling me how many number of states are available per unit energy, then those bands would look something like this. This is the band gap. So all this comes out of the band theory of solids. Okay, free electron-like picture cannot give you, however successful it is, it cannot give you the existence of band gaps in the system. I'll return to this idea a little bit later in a somewhat different context. But once you use the band theory, one can ask about what is the nature of the wave function of these electrons which are moving around in these bands, which are because of this periodic lattice. Now, these in some systems, you can think of that the wave function has a self-rotation about its axis. As the electrons are moving around, the wave function has a self-rotation, and that actually gives an important property to the wave function, resulting in interesting physics. Okay. Now, when you think of these, electron wave packets or electrons moving around in bands with this property that they are rotating about themselves, you can actually try to ask, what we know of solid state physics that's there in Kittel and Ashkrafton-Mermin. So if you know your basic semi-classical equations, yeah.
Mandar, before you go into too much specific.
Yeah.
So do the spins interact, and is that important for the band gap?
No, for the band gap, it's just so there can be some additional band gaps or modification of band gap because of the spin of the electron. This is just for the fact that the landscape in which the electrons are moving around is corrugated. It's not flat. So a flat situation does not result in band gaps like the one I sketched. So spin and other kind of flavors or degrees of freedom will add some gaps, but we're not talking about that yet.
Okay, but that does happen.
Yeah, that will. I'll point out the connection to this work, but this is not needed for what I'm talking about today. Okay, so what this is, looks like a complicated equation, but this basically is an equation which tells you what is the kind of the group velocity of these wave packets as they're moving around in these bands. It's just the gradient of the energy with respect to the momentum. And if I want to describe a kind of semi-classical equation of motion, this tells me how the wave packet moves around. And if I apply some electric field, I can also, I don't know, it's a very simple idea, but it tells me how its momentum is changing because of applied electric field or a magnetic field. Okay. Now, these semi-classical equations have been in textbooks for a long time. What they did not account for is this certain solids have this property that the electrons have, wave function have this kind of churning aspect to it. So now with the addition that there are materials, I'll qualify in which materials the wave function has this churning kind of property. But because of their churning, what happens is as the electrons are moving around in the solid, there is a kind of a Magnus-like force. So the electrons in these solids will get deflected to one side, much in the same sense, if you hit a soccer ball, or if you watch, sometimes it will get deflected in a particular direction, and that can be associated with this churning aspect. So what is the consequence of this is that, so this idea and understanding of this has all come together in the last 15 to 20 years, and there is a correction to this classical equation that you may have solved in one or known how to derive in solid state physics, and this is this term. And this, you don't have to worry about the exact relation, but the fact that this term is non-zero has very important consequence, which is that, as you can see, this is a equation for the velocity. This tells me that there is an additional contribution to the velocity. Which just comes from what is the arrangement of atoms inside the solid. It doesn't depend on anything else. It's the symmetry of the lattice that provides this velocity, which is called the anomalous velocity. Now, the important creature is this with omega sub n, which is called Berry curvature. It's kind of I'll talk more about it a little bit. It basically provides the impetus for these deflection, which results in an anomalous component of velocity. Okay, without applying magnetic field. So if you're thinking about, this does a kind of job like magnetic field. You have a Hall effect. If you have a 2D conductor and you apply a magnetic field, electrons get deflected. This Berry curvature does the same job, analogous job as that of magnetic field, but there is no magnetic field here. In the absence of magnetic field, but just due to the arrangement of a particular specific arrangement of atoms. And the qualification is here is that if inversion symmetry of if you make a transformation R going to minus R for all the atoms in your lattice, if you come back to the original lattice, it means it preserves inversion. If you just take R and you atoms coordinate and you make it minus of X, minus of Y, minus of Z, if you get back to the original crystal, it preserves inversion. If the crystal doesn't come back to itself on inversion, this Berry curvature is non-zero. Okay, so it's easy to identify where this term will play a role. So a large class of materials from their intrinsic symmetry turned out to have this Berry curvature zero, so you don't have to worry about, and that's the origin of why these equations in textbooks didn't include these terms, but the newer textbooks which take care of all this physics in a more comprehensive manner, will say that there is this term. Yeah.
Could you actually enumerate a little bit physical insight into this omega of A? Because you said it's something to do with the geometry of the structure.
It's the symmetry of
the structure.
Yeah, so let me give you an example. Let me start with an example which I will refer to a little bit later. But let's say I have a honeycomb lattice, which is like this, and I have carbon atoms, okay, everywhere. Now, this is basically the structure of graphene. And now, if about this center I do the transformation, which is R going to minus R, okay. Then this guy will transform to this location, this will go there, and so on. You get the original lattice back again. Okay, so this will not have Berry curvature in the system at K through all the momentum space. But now let's same crystal structure, but I make boron nitride, which is isoelectronic. Pairwise, if you take boron and nitrogen either side of carbon, they have the same number of electrons as two carbon atoms. But the moment you make this boron and nitrogen and this kind of crystal structure, and you say, is this crystal structure inversion symmetric? And the answer is, it's not inversion symmetric. You get a honeycomb lattice, but what happens is you don't match the exactly same lattice. Boron will replace nitrogen, and in terms of the symmetric properties, it's not the original lattice and it's not the same. So it breaks inversion symmetry. Okay. As soon as this is there, I don't want to go into how the Berry curvature is calculated. It's pretty simple. We teach a course where we calculate, but that's probably not sort of appropriate for today's class. But it really literally does measure exquisite properties of the wave function of the electron when it's moving around in solid, and the wave function respects the symmetry of the lattice. Okay, that's the essence.
So if there are impurity in the lattice, there can be also misconnecting, right? So can we observe this effect there?
Almost all of the physics that I will talk about doesn't care about disorder. Even if there is disorder, it will not change any of the physics. So it's one of the powerful parts about this kind of physics is that it's robust against disorder. So even if you have disorder, it will not radically change. Of course, if the lattice itself is no longer meaningful, you have defect all over, then you can't talk about these symmetries that I talked about. But as long as there is some semblance of order, the disorder is limited, nothing will happen to it. It's still valid. It's still there. Okay.
The other part to it is the k dot term. K dot shouldn't it be velocity change?
Yeah, but because of this equation, if you have zero magnetic field, you can replace k dot with electric field.
Okay.
If you say you don't have a magnetic field, then it's just an applied electric field in your system. You apply, to measure a current through the system, you apply a voltage, which is basically giving rise to an electric field. So you can think of this equation as just electric field times the Berry curvature.
Okay, fine.
Okay. So it provides an anomalous velocity and it deflects the electrons to one side. So if this is your sample, you apply the electric field here, the Berry curvature is pointing up, then electrons get deflected to one side on their own without applying any external magnetic field. So this Berry curvature is a very important way to think about band properties, and it relies on knowing about the wave function of the electronic bands. Now, the other number that I will refer to is called the Chern number. Okay, it's it's an important way to talk about the topology, and I'll make this connection in our next few slides. But since I'm talking about a physical meaning of Berry curvature, the Chern number is basically kind of an integral of the Berry curvature over the Brillouin zone of the inside the solid. And typically, if I start with a two-dimensional material, I have a Brillouin zone which has symmetry. The lattice has translational symmetry, so I basically wrap it up, and I have a cylinder in one direction, and I wrap it up again. I basically get torus. Okay. And this Chern number is essentially for electronic bands. It's the integral of this Berry curvature over the whole band, and it's basically some multiple of 2 pi. Okay, if the Chern number is 0, then typically people will refer to this system as topologically non-trivial. If you want to, small changes in the system, and I'll illustrate in the next, will not affect this Chern number. So, for example, disorder will do nothing to the Chern number of a system. It reflects intrinsic band properties. It doesn't care about disorder. Okay, so this C is an integer and reflects sort of a very intrinsic property of the bands of the inside the system. So when is it non-zero? Typically, the Chern number is non-zero when you break prime reversal symmetry. So one easy way to break prime reversal symmetry is if you apply a magnetic field, then you prefer one. If you apply a magnetic field, then you if you have current flowing in one direction, then the magnetic field sort of chooses one current direction over the other and breaks time reversal symmetry. The electrons going one way and the other way are not equal. So that's one way to get a non-zero Chern number is to break time reversal symmetry, or there can be something inside the system which spontaneously breaks the symmetry, time reversal symmetry, and then you can get a non-zero Chern number as well. Now you may say, okay, this is all boring. What is the implication of it? The implication of these systems is that then if you have a system which is an insulator, so the yellow sort of shaded region is a state where this is a real space map of your, let's say, piece of material. Then yellow means it doesn't conduct charges at all. Okay. What a non-zero Chern number basically means that because of the fact that it has non-zero Chern number, automatically there is a one-dimensional path, which kind of a loop, which will allow electrons to flow around while the rest of the material is an insulator. So it's sort of like a one-dimensional loop sitting in the on top of an insulator, which allows the current to flow around. Okay. If the Chern number is an opposite sign, it means that the current flows in the opposite direction. Okay. And there can be situations that I will talk about where there are indeed edge states, boundary modes, where there is two boundary modes which are circulating in opposite direction, but they kind of cancel off. So the net Chern number is 0, but these kind of systems are also topologically interesting, non-trivial. If you're familiar, these are also kind of systems where you get constant Hall physics, and also the physics that I will talk about later has connection. The overall Chern number is 0, but they're still topologically and interesting.
Just a quick question. These vectors that you have drawn, the arrows, are they the velocity of the electron?
It's the circulation of these modes. They will only, so if you put an electron in that, they will only move in one direction. They will not move in any other direction. Okay, so it's indicating sort of if you what would be the path of the group velocity direction of the electron
Velocity of the
these boundary modes.
Yes.
Okay, so this has if you know about quantum Hall physics, these are basically these quantum Hall systems are basically systems where by applying magnetic field you break time reversal symmetry and you get these edge states in quantum Hall. Turns out a lot of the topological physics came out of this idea that without applying magnetic field, is there some intrinsic property of the material that will give rise to these boundary modes which are interesting? Yeah.
Yeah. So does the Chern number have any relation to the velocity of the electron?
No, it doesn't tell. Okay, that's a good question. So Chern number doesn't tell you any of the other details. It's an integer. Okay. So it just tells you how many. That's why I drew the cartoon. It just tells you how many of these edge modes are flowing around. Okay. It doesn't give you information about what the velocity is. Nothing.
Okay. So the reason is this trajectory that you have written. Would it be essentially fundamentally different of the very?
It's related to this very curvature.
Which means it's independent velocity voltage.
Yeah, it doesn't tell you anything about details of the velocity, but it arises from the structure of the very curvature, how it's distributed inside the momentum space of the solid. Okay, so it's it measures. In the next slide, I will make this connection to other physics a little bit clearer. Okay, so I should say a little bit about why this is interesting. Is that these systems, they don't care about somebody said about disorder. So if I have a edge state which is going around like this, then I take a bite out of this and I chomp this material. I cut a whole bit out of it. This system doesn't care about this, the fact that it's no longer rectangular thing. It will just form it has a boundary mode irrespective of the geometry. You have a scatterer here which scatters electron. It will not affect this boundary mode at all. The boundary mode, it has a protection because of the intrinsic physics. The motivation for these kind of edge channels is these are robust against scattering. Okay, so if you want to move charges from one side to another in a material and not have to dissipate energy, then these are your kind of super highways for the electron. You put them here, they move from one side to another without undergoing any scattering. That robustness comes from this intrinsic symmetry of the lattice and the topology, which protects and this which prevents this scattering. Okay. So now let me. There are these. And I'm not an expert in topology, but I wanted to make this connection. There is this you can do this kind of a simple calculation for magnetic field. You kind of try to essentially sum out the flux due to a magnetic field, and you can quantify in terms of an integer, which is the magnetic charge. This Berry curvature has the same structure as that of a magnetic field. It gives rise to a Chern number, which is an integer. It's also called another name, which is called PPN invariant. And then in mathematics, in topology, you can look at the curvature of any surface or a manifold, and that is also this is Euler characteristic, which is in this case an even integer. All these are essentially part of the same class of physical quantities, which are they are all the same mathematical structure, and they're basically fiber bundles. And you might have seen in cartoons, and when you hear talk about, you will see a cup and with a handle drawn, or a donut. These are all essentially surfaces where you have one hole in the system. Then a cup is equivalent to a donut. This is kind of cliched kind of figure that everybody shows in these talks, and that was the reason why I didn't want to show it, but I want to make connection. So these are mathematically equivalent because they have only one pair. All that has happened here is you have pressed one side of it and made a large dimple, and this hole becomes your handle. So they're mathematically equivalent. They're the same surface, but just deformed. So that deformation will actually not fundamentally change the system. A topological transition will happen if I have a donut or a vada, I poke another hole inside the system. Then I basically go to a completely distinct topological system. There is no way to continuously deform kind of a vada with two holes by slowly pressing. Without closing this hole, you cannot go to a cup. Okay, so this comes from sort of deep and fundamental ideas of mathematics, and they have connection to condensed matter through this idea of Berry physics, which is Berry curvature, and kind of as integral of the Berry curvature in a kind of momentum space gives rise to this Chern number, which is an invariant of the system. All right. So where am I? I'm going fairly slowly, but let me. I told you about Berry physics and sort of the connection to topology, and the main takeaway message is it's just the arrangement of atoms which embodies the interesting property to the electron wave function.
So Mandar, I have a question.
Yeah, sorry. Yeah, I know who that
So yeah, it's Amit.
Yeah, I know.
Yeah. So how this putting one hole in the donut is equivalent to the topological transition of the condensed matter?
Because the Chern number will change. So if you want to think about the Euler characteristic, that is going to change for a kind of a donut with two holes. So that's analogous to having a different Chern number system. Does that make sense?
Okay. Yeah, I got it.
Okay. Let me get started on the next part, which is still we are talking about the pedagogical part, which there are a lot of interesting questions. Let me. So we have atoms in a solid. So way back in 60s and 70s, people thought I want to essentially do the same thing. Different atomic arrangements are different. How about we make a different arrangement or different periodicity by essentially engineering material, essentially making alternate layers of different materials. And this is a famous sort of quantum mechanical problem that you solve in some course in quantum mechanics. You have a periodic potential which is repeating over space, and this is sort of the chronic penny picture. And so people realized in 60s and 70s you can actually make structures like this, and they look something like this. This is the cross section of you have a wafer which is two-dimensional, and you look at the cross section of it. It's not just homogeneous, but it has alternating layers of semiconductors, and the length scales are clear. Now, this semiconductor, which could have semiconductor A and semiconductor B, gives rise to an entirely different semiconductor with new additional electronic properties. So people figured out this, and it led to a lot of the key discoveries like the cascade lasers, different kinds of electronic devices. So this structuring over space is called superlattice. So this is the original atomic lattice, and lattice which is larger length scale than the atomic lattice is called superlattice. That also modifies the electronic properties of the materials. So this idea is old, and what the Proostronics field does is it actually puts a new twist on it. And what it does is, if you have one two-dimensional material, you put another two-dimensional material, which is a relative angle. So you have the original atomic lattice, but the twisting angle controls the next periodicity, next level periodicity that you get. This is called the moiré periodicity, and that essentially you can think of it as a scattering of the electronic wave function. It modifies the overall system's electronic property. It's no longer equal to just the two layers of the material. So it's the same trick of superlattice to modify electronic properties, but it's a fundamentally different way that you are twisting, and that angle control has radically sort of powerful tool for controlling the electronic properties. I'll give you a glimpse of that. So this gives rise to superlattice. Angles control the periodicity. As you could see in this cartoon, as I change the angle, the length over which the superlattice exists changes, and at a very, very small angle, that the periodicity is large. It's inversely proportional to the twist angle. So there has been a lot of buzz in this field since roughly about 2018, when the first set of papers came out. They're based on some prediction of primarily, there were a bunch of different papers, but a lot of work has been done by Alan McDonald and his, that time postdoc, Rafi's sister. But experimentally, people realized this by twisting layers of graphene. So they could start with 2 layers of graphene and realize what is called a correlated insulator. It's all carbon, but it kind of mimics materials that people have been studying for decades, but it consists of other elements where electrons are strongly talking to each other. And not just that, it leads to superconductivity in something which is only made of carbon. No other superconducting material is there. So, magnetism. Magnetism arising from just carbon, which seems like a sort of very strange idea, but this magnetism has connections to this idea of topology, and sometimes also referred to as an orbital magnet. So it has given rise to a lot of excitement in the field. And what it basically, where does it come from? So if I take a single layer of graphene, it has a band structure which looks like this. This is energy, this is momentum. This, roughly this is of the order of electron volts, from this point where the bands meet up. But most of the times when we do the physics, we essentially do expansion or low energy effective Hamiltonian around these points, this high symmetry points. That is sort of the essence of all of this exciting physics, is that it looks at a certain energy subtext, or the fine print in most of these experiments is that there is an energy interval over which this Hamiltonian is a valid description of the system. So once you have that, if you twist it, you basically get another Brillouin zone, which is rotated by the same angle of the rotation of the original lattice in the real space, and that periodicity, superlattice periodicity, gives rise to another Brillouin zone, which is called the moiré Brillouin zone, which is this. And what happens here is that if you look at these points, you have a Dirac cone at each of these red and blue. They come close to each other because they're rotated by because of the rotation. And when they come close to each other, they will actually hybridize when they overlap. And the moiré zone will actually have regions which are basically this part, which is electronic states which are flat, which don't have much spread. Just to give you an idea, this spread is about roughly 1 few MeV to about 10 MeV. It's controllable in systems with angle or some other knob. Okay, so these flat bands.
Is this under the limit that the set of free electrons on both the lattices are not strongly interacting?
No, they are interacting. If they don't interact with each other, then you won't get this physics. The fact that the exciting physics happens only because the electrons are hopping between the two layers. If you say that they are electronically decoupled, you basically get two copies of this and none of the exciting physics. The fact that electron has to hop from one layer to another in different sites causes this hybridization. So in the language of chemistry, the fact that you have electronic states here, but they cross, but interaction hybridizes these
So
bands.
that those gaps are basically some sort of a coupling between the.
Yeah, it's because of the coupling.
And how large can they be?
I mean, the gaps are of the order of roughly again 10 milli-electron volts.
10 million.
Bandwidth, which is the width of these energy states, is about 10, roughly 10, and this is 10. I'll not talk too much about it. So often when I talk about this, people are curious that how does one make this? It's actually somewhat subtle because you cannot arbitrarily pick up two layers of Cooley material which are 1 atom thick and align them to an accuracy of 1 degree because you want this angle to be very, very small. Okay, I guess I didn't say something here that this flat bands arise when the hopping between the interlayers, the layers between two layers, and the hopping between sites in the same layer become comparable. That's when the flat band arises.
And a quick question again, going back to the picture, where does the angle really matter? Because we can also tune the distance, right?
Good question. No, so okay, so the distance between the two layers is a knob that has been little explored. Right? It's hard to control in experiments.
Okay.
Angle is very easy to do.
Okay.
People have done experiments by doing hydrostatic pressure. So you make this layer, you put it in very high pressures, 100 atmospheres kind of pressure. Then this gap changes, and then this hybridization of the bands changes. So it has been verified, of course, but that knob is hard to do in this system.
So it's easier to twist it?
It's easier to twist. That knob is a viable knob. Pressure means you make the device and you try to vary the pressure. It can be sort of destructive for the device. Okay. Right. But the idea has been checked, and some people work on it. That idea as well, but that's a knob that we don't work in. So we want small angles. Arbitrarily, it's not possible to find two pieces of graphene or any 2D material and rotate them to 1 degree. So what strategy that other people in the group, other people in the world figured out, and we kind of emulate with some different variant of fabrication that is to start with one piece. Then you know exactly all of it isn't aligned, kind of full registry. It's a single crystal. Then you actually cut it into 2 pieces. Then you know that there are 2 pieces of the crystal which are copies of the same thing. Then you this light blue material is boron nitride. You pick up 1 piece of it. Okay. So then you know that these 2 are aligned. Now what you do is you rotate the bottom remaining piece to a precise angle, what you want using a mechanical rotator, so you know what the angle is. Then these 2, you have a precise relationship between the twist angle of these 2 materials, and when you bring them together, you can make a sandwich, or what we call colloquially a stack. It's a stack of 2-dimensional materials. And then one can make devices out of it. So I should say that this twisting realizes a kind of artificial 2 layers which are not thermodynamically stable. So you have to vary them a fair bit. Sometimes the angle in the actual device doesn't turn out to be the angle that we dial. Okay. So, but you can verify what actual angle is in the device, even to an accuracy of something like 0.02 degrees from the transport measurements. Now, this requires, it's easy to describe this, it requires a lot of skill, and I don't have that skill, and my students and group members have this, requires a lot of patience to build a stack like this. It can take several days, okay? So to get to this stage, this has already something like 5 layers of picked up sequentially. It requires patience and perseverance. So this is 2 examples, and the length scale. Now these are right for making devices, and I've shown this video, kind of video in earlier talks. So this is some how do you make electrical connection to a piece of graphene? So this is 1 atom thick graphene. These are thicker pieces of graphene. This is very thick graphite, something close to 100 plus nanometers. So if I want to make electrical connection to it, I use the process which is sort of developed in semiconductor industry. This video is not working. Okay. Nevertheless, if you have a question later, I can explain this to you. But you can make deterministic electrical connections for it to do measurements. That process itself also takes another couple of days. For particularly, this doesn't have that sandwich, structure. So it takes some time to make it.
This system where you have multiple layers, are they all kind of twisted by the same angle relative to one another?
No, this one is just a chunk of graphite.
Not this, but in the system that you described earlier, where you have multiple 5 layers,
Yeah.
is the twist angle for each successive layer the same as for the previous?
No, so thanks for that question. So we care about only the twist angle between the layers, typically the layers of pieces of graphene or 2 layers of graphene. We don't, that's an important knob, but today's talk will not. The relative orientation of the insulator, the light blue colors, which I showed you earlier. This light blue is an insulator, hexagonal boron nitride.
So this is just a 2-layer object now, 1 twist angle between the 2.
Yes,
That's
yes.
it.
Yeah, the other is kind of a encapsulation, if you like, to protect this twisted thing. This is also a knob of relative rotation between the blue layer and the black layer of graphene. I don't want to get into it today because it will get quite complex. Yeah.
Does the gap between the 2 determine the twist angle? I mean, would you have any relationship to get you the binding that you?
No, the gap doesn't determine, physical gap doesn't determine the twist angle. The twist angle you have to kind of dial in this stage. I rotate the motor, some geared stage by 1.01 degree, 1.18 degree. I get that twist angle. But the spacing is I bring it close and I eventually let go of it. First, I have to kind of press it a bit, but eventually it has to stay on its own. So it will thermodynamically reach some equilibrium spacing of between the atoms. These are actually very important questions, but there are subtleties that if I'll talk to you afterwards. If I give that, that will take a lot of time and nuance to it, but we'll talk more. Yeah. Angle? Yeah, of course. Which planes? Yeah. They are like, if you like, 2 pieces. If this is 1 layer of graphene, I can have directly aligned, or I can rotate it. Or tilt. It's an interesting question. No, it's as flat as possible. There can be some imperfections inside the system, like trap, bubble, air gap in between 2 layers, but they're flat because we eventually let go of them. Initially to bring them in contact with pressure, but they're after that we do a lot of processing. So they're we don't have that would be actually an interesting experiment, but we don't have a way to control the tilt. Okay. All right. So we can make electrical connections, and then these are ready for measurement. So I kind of taken a fair bit of time, maybe 18 minutes more than but I gave you an idea of what this field is and what is exciting about it. Now I'm going to shift gears and talk a little bit about our experiments. This will be a little bit more technical. If there are any pending questions about the last part, maybe you can ask me now. I'm happy to answer. Before I shift gears a little bit. Anything about how these devices are made or what makes them interesting, I can explain now. Yeah.
I think you mentioned this, when you put the 5 layers, so 2 layers is angle and that is you explain, but 5 layers, what is the advantage or disadvantage?
So okay, so it's more of encapsulation. So the boron nitride that we use is which has crystal structure is near identical to graphite. It's a very good insulator with a band gap of about 6 electron volts. Graphene is a semi-metal. So when you encapsulate it, when you make an electronic device, there are things called traps, which dangling bonds in chemistry terminology, which can electrostatically influence the flow of electrons in the layer that you want to study. If you use a material with a high band gap, it doesn't have dangling bonds, boron nitride, and so it makes it actually a better electrical. If you put it on silicon oxide has a lot of defects and dangling bonds. It impedes the ability of the electron. The mobility of electrons will get reduced. That's why we, at the bottom and top, we sandwich it in boron nitride. Okay. So right now, for the purposes of today's talk, boron nitride is a bystander. But it plays some role, but I don't want to go into it today because it makes things needlessly complicated.
So I'll just actually about to ask you that. So if you have 2 heterogeneous thin films, your hydrogen properties will change, right? I mean,
Yes.
So how much of that can you actually capture in your system, and is that in
If I instead of taking graphene, I take material A and material B.
Yeah.
Yeah. So that people are doing it, and you can actually realize new properties or functionalities by using these are called the terminology in the field is called the same material if you use, it's called homo bilayer, and if it's a different bilayer, it's called retro bilayer. Okay, people are looking at it. That's another knob in this field. Okay, so let me get started with the remaining part. So I've mostly positioned the talk in terms of graphene, but there are graphene family is wide. The system that we find more interesting is a system which is 2 layers, starts from 2 layers. The main building block is 2 layers of graphene, which is called bilayer graphene. So bilayer graphene is very interesting that it's a semi-metal, much like monolayer graphene, but it's a tunable semiconductor. So if I take a layer of 2 layers of graphene like this, and I make a device, and I apply a perpendicular electric field. Okay, just put it in between 2 electrodes. The moment I apply electric field, I actually break a symmetry inside the lattice. I break what I told you is the inversion symmetry, because effectively the cross section of a bilayer graphene will look like this, with atom here. In the absence of electric field, if you do inversion, this is all carbon. You go back to the same lattice. But the moment you apply a vertical electric field, then the potential here and the potential here is actually not the same. And you break inversion symmetry, and that basically produces a band gap. So in the same material, you apply a perpendicular electric field, you can actually make it a semiconductor, up to something like people have demonstrated 150 milli-electron volts of band gap. And that arises from this simple idea that applying electric field makes the environment of this atom and this atom inequivalent, and that results in a band gap. And that's the starting system that we use in our experiments. The reason is this, that its band structure is tunable. So this system gets around this idea of twisting to a particular angle because you have another knob, electric field, to tune its properties. So the first kind of structure that we can make out of it is kind of twisted bilayer. Mother material is bilayer, you twist relative to each other, and you get similar flat bands, but an additional functionality is there that if you apply electric field, you can vary the bandwidth of this system up and down by applying just the electric field. In the same device, you can tune the bandwidth. Today, I'm not going to talk about the physics of correlation, but tuning the bandwidth is a way of positioning the system in different states of closeness to a correlated state, because ratio of its kinetic energy and its potential energy, is basically connected to this idea of what is the Coulombic interaction energy and the bandwidth. Okay. I won't talk today about physics of correlation. This is a wide area. I'm going to focus today about what is interesting topologically. That is our primary focus in our research group.
Can I ask a quick question?
Yeah.
How much electric field do you have to put to get 150 millielectron volt of change?
So you can apply electric fields with this boron nitride. You can apply electric field of the order of 1 volt per nanometer.
1 volt per.
Okay, so I don't remember the exact number, but you can safely apply that kind of electric field. It's pretty strong. So people have studied a lot of correlations physics in these systems. What happens is that physics of correlation arises because you have these flat bands, which I sketched earlier. You have these bands, flat bands. This is energy. Then when it's exactly half filled, this band is exactly half filled. The interaction between the electrons spontaneously, results in a gap, which is, I would say, a correlated gap, and that happens because these systems have flat bands. So they are behaving like some other complex material that people have been studying for many years. But here it's all carbon. Only thing is you have exquisite control over the bandwidth relative to the interaction energy scale. So people have studied a lot of interesting physics with this, but our interest is in looking at physics of the Berry curvature and largely studying that physics. So this is what our device looks like. And when we do electrical measurements from this device, we can vary 2 experimental knobs. We can measure resistance, which is essentially applying voltage and measuring the current, or the opposite, applying current and measuring the voltage. And this is what the device looks like. We have 2 gate electrodes, one gate electrode here, another gate electrode here. This is one way to realize the gate electrode, but there are other ways. So what that does is that it provides an independent control of charge density in the device and electric field. So it's a very important distinction that charge density controls, in physics terminology, controls the Fermi energy or doping, and the electric field is an independent control. Because these materials are susceptible to this band structure modification because of the electric field, this is an independent knob that you have. So you can control charge density and electric field independently. Okay. So what you see here will become clear in a minute. So this was some earlier work. The first work that we did was a collaboration with Rajdeep and student Umesh, which allowed us to understand. So when we measure the electrical transport, this cartoon is what we can focus on. So this band structure is something like this. I have one flat band or 2 superimposed flat bands, and then 2 bands, remote bands, which are widely moving in energy, something like that. So this goes on for, but then you have a set of states which are narrow in energy. Now, if you apply an electric field, which is basically moving up and down, it will become clear. You actually slowly, these 2 bands which are overlapping, you open up a band gap in between, and then further band gap. Eventually, these 2 bands will move, and it will become a sort of somewhat merged. The flat bands will merge with the remote bands, and there will be a large gap. And the electrical response is these gaps that you see here at this energy. These are the gaps due to the moiré periodicity, which is the additional periodicity that we have. And this direction changes the electric field. Here it starts with a metal somewhere here, and then you open up a gap. It becomes a semiconductor, which is showing an insulating response. So these systems also have Berry curvature. So you can calculate their properties. You can calculate their Valley churn number, which is there are 2. I didn't get time to elaborate too much on this, but in the graphene world, there are 2 valleys which are fundamentally inequivalent. and they have opposite Berry curvature, and the churn number are opposite. So the main takeaway is that these systems have large Berry curvature, and these Berry curvatures, as I told you, give rise to an anomalous velocity. And that's something that we probed in the first experiment that I'll quickly talk about. So this is the term that I showed you. Yeah.
That's a very main question. To begin with, the Berry curvature is uniform across the surface.
No, so I should make it clear that Berry curvature is a quantity that we will talk in the momentum space. We don't talk about in the real space. It's not uniform. It has patches which are more, by Berry curvature of a particular sign, and then in a different part of the case the Berry curvature sign could be different, but it's non-uniform in momentum space.
So what determines it to begin with, even before you apply it?
It's actually just the symmetry of the lattice. The fact that you have two standards, you have different kinds of hopping possibilities for the electron from one side to hop. That determines the distribution of the Berry curvature in the momentum space, if you like. It's just the arrangement of atoms.
Okay, so when I was headed is, for example, if you apply a specific field, to be able to predict the Berry curvature.
Oh yeah, these are all calculable quantities. I mean, I should say that there is some caveat. People are still understanding some nuances of how this hopping, some details of hopping. But there are models which you can calculate. For example, Rajdeep does a lot of these calculations. You have to take them with some quantitative precision. Is not something you should ask of them. Maybe Rajdeep can say a word, but they indicate the distribution quite well. Rajdeep, do you have anything to add to that?
Yeah. So, yeah, most of these models, I mean, they may not be very accurate in terms of energetics, but these are topological things. So, they are reasonably robust. You make small changes, these kind of distributions will not change by a lot.
Yeah.
So, you can trust these kind of things out of this kind.
Yeah. So it's just as I said, because the properties arise from the basic symmetry properties, they don't radically change, but it's hard to be quantitative. That's something that people who ab initio are working to develop better and better descriptions for these systems. So in these systems also this anomalous velocity plays an important role. So if you make a device out of twisted bilayer, like I showed you, a twisted double bilayer, you can actually characterize its Berry curvature. So these kind of experiments, what they will do is if you send a charge current, because the two valleys have opposite Berry curvature, electrons of one valley which are of a particular flavor, let's say blue, will get deflected to one side because the Berry curvature provides one kind of anomalous velocity, whereas the green, which is electrons belonging to the other valley, will get deflected in the other direction on their own, just because the material has that symmetry. And then in this direction, you get no charge current, but a current flowing of the valley degree of freedom. It's like saying spins of one, there's a quote net spin current in this direction. The valley degree is very analogous to the spin degree of freedom. It's much more than that, but it's easy to sort of make that connection. So when the valley current goes down, it actually gives rise to another opposite inverse effect, which is called inverse valley. Because you're sending a pure valley current in this direction, because of the Berry curvature, it will generate a voltage, which is a way to detect the presence of the Berry curvature. And that's sort of what we did, and we showed that this Berry curvature is kind of tunable with electric field. So for that, we do experiments in sort of two main geometries, which are called local. Let me just go back a little bit. Local, I send a current in the outermost loop and I measure a voltage. This is called local. This is called non-local because I send a current in this arm, and largely because of Ohm's law, most of the current will flow here, and actually the current that is flowing here is actually exponentially suppressed. It's not mathematically zero, but it's exponentially suppressed. And if I measure a voltage difference far down the line here, then this contribution of the normal Ohm's law will actually be close to zero. It's very, very small. And the moment that this signal is becomes large is an automatic indication that there is Berry curvature physics. So we do this measurement in this is local resistance, this is non-local resistance, and that non-local resistance is large precisely where the gaps are large. And that's precisely the location in energy where Berry curvature is large. So that's why you see non-local signal large. And everywhere else here in the middle of the band, here you have lots of electronic states, but no non-local signal because there's actually very, very feeble Berry curvature. And that sort of just a line slices to show that this non-local signal, which is arising from the Berry curvature, is strong at the band edges, and it's tunable with the electric field. Okay, so this is in terms of devices. People think of this valleytronic degree of freedom as a kind of new devices. People know spintronic devices is exactly analogous, but using the Valley degree of freedom. And in terms of physics, why this is interesting is because these systems now open up a knob to tweak around or play with the Berry curvature, and possibility of some interesting devices exist. So I'm running behind quite a bit. I'm gonna go a little bit faster. How much time can I take?
10.
Okay. All right. So let me. I won't have time to talk about the last part. If you have questions, you can. So I'm gonna. This is sort of a really exciting result that we recently sort of figured out and understood. I'm going to talk about that and stop at the end of it. So physics of correlations has been studied quite a bit in this, and if you pick up, Nature or Science or some Nature family journal, you'll see a lot of work on correlation physics from these materials. But something that has not been explored as much, and I certainly find it more interesting, is that these bands have very interesting topological properties. Okay, so there has been a lot of theory work across the world that Rajdeep has explored this quite a bit. You can have situations where the Chern number of the system actually undergoes a change by applying this electric field. You modify the potential that different sites feel that changes the topology of the system. And this is the reason why we started exploring these systems to look at the topology. So this is interesting because people have been studying topological transitions quite a bit. Quantum Hall, as I told you, is sort of the mother phase that people study quite a bit since its discovery in 80s. You go from one gap in the Landau spectrum to another. You basically change the Chern number. So you can tune the Fermi energy and you can go in different states. But none of the systems so far have used the electric field to actually modify the material and look at topological transition. And that's sort of what we wanted to look at. So it's very hard to detect topological transitions in systems which preserve time reversal symmetry. So this is an example of a system that breaks time reversal symmetry, which is quantum Hall physics. And we used a particular quantity which is called the Berry curvature dipole, which is the first moment of the Berry curvature. So you have Berry curvature distribution in the moment of space. The Berry curvature dipole essentially measures the Berry curvature first moment and actually reflects the topological transition. So I'm going to go through this a little bit fast. So if you have a completely symmetric lattice, you have opposite Berry curvature hotspots, and you can look at the Berry curvature distribution along three principal symmetry directions, and you see that they lie on top of each other. If you have a perfect honeycomb lattice. However, if there is some strain, some distortion in the original lattice, what you'll see that the Berry curvature is somewhat different, though the magnitude of the Berry curvature itself is not radically different. But if you look at this physical quantity called the Berry curvature dipole, it reflects even the smallest of changes in the Berry curvature that is distributed inside the momentum space. So for this, there was an idea which is very powerful idea, which was Inti Sullivan and Young Fu came up with, is this concept of very curvature dipoles. This is a mathematical relation that it basically measures the moment distribution with respect to some high symmetry point in your lattice. So for now, just ignore. And now, if you plot the very curvature dipole, so this plot shows the distribution of the very curvature in the case space. This is energy. You have negative, positive, and this is the quantity which is called the very curvature dipole. Now, the dotted line is when everything is symmetric, which is this blue lattice. It's exactly honeycomb. It's identically zero, the very curvature dipole. But if you now measure the very curvature dipole in the strained lattice, it's not zero. In fact, at certain points where the very curvature is large, the very curvature dipole, which is the first moment, becomes quite large. Okay, and that's what we focus on. Instead of measuring the churn number, which is measured with topological condition, which is very hard to do. You use a quantity which is related to it, which is the very curvature dipole, and it tells you whether the system undergoes a transition into a different topological state or not. And all this is at zero magnitude. So the moment you have a non-zero very curvature dipole, you get an interesting physics that if you send a current in a device like this at a frequency omega, because of the presence of this very curvature dipole, you get a voltage in this direction at frequency 2 omega. It's a kind of nonlinear effect, or called the nonlinear Hall effect, and that reflects this very curvature dipole. And what we do is, in a sense, measure the very curvature dipole through this nonlinear Hall effect. So this quantity in orange is the V2 omega xy. Xy reflects the Hall signal. So we can measure the nonlinear Hall signal as a function in the parameter space. So this is the resistance. Simultaneously, we can map the nonlinear Hall signal, and that's what we will use to extract very curvature dipoles. So this is how this nonlinear Hall signal is actually modified by electric field, because we have independent control. And so what one does is basically, when you apply electric field, you modify the very curvature distribution, and that as a result modifies this very curvature dipole. And the way to extract this very curvature dipole is to do this kind of a measurement. You measure the experiment and then you do the scaling analysis. Okay, so this is the Hall signal magnitude normalized with square of the nonlinear voltage. Gives you this kind of scaling relation, and this B is a measure of the very curvature dipole, and that's sort of what we did. So we measured this property V2x V2 omega xy divided by this as a function of electric field, and we also measure sigma xx square, which is this quantity, and then we do a parametric plot. And so our sort of key innovation was this scaling relation becomes complicated because of other kind of scattering. So people mostly do this kind of experiment with temperature, and that makes analysis complicated. We did this at a fixed temperature by just varying the electric field. And if you do a parametric plot, essentially remove the electric field and plot, combine these two, you will see a plot which comes out like this. And if you do the scaling analysis here, you see the intercept here for this up to this point is 1, and then as you go past this point, it radically changes, in fact, flip sign. Okay, now that is, as I will show you in the next slide, is basically the very curvature dipole changes its sign, and this point is actually a point where the topology of the system changes, the churn number of the system changes. So we skip this. We characterize how the very curvature dipole is as a function of doping. What is happening, and this is maybe the last slide because I'm running out of time, is that as you change the electric field, these flat bands will touch the remote bands, and the very curvature flip sign. And after that, the churn number, the value churn number of the system undergoes a change, and that gets reflected in the very curvature dipole. Okay.
So Mandar, is your change by
3 from -1 to 2 because that was kind
Yeah.
of a prediction from theory.
Yeah.
You actually see
Yeah.
-1.
I mean, we can't, okay, so I should say that in this experiment, we don't measure the churn number. We don't have access to churn number. Okay, that problem still remains, but using the verification type allows me to see that condition. Right? I believe these numbers are matches what you
And others.
and others have Kushino and all people have predicted. So by measuring the Breakaway dipole, I see a topological transition, and this technique as the first demonstration of using the Breakaway dipole to detect. There were some theoretical ideas that existed before, but we demonstrated that this could be powerful now. And I think I'll stop at that point and take questions that you might have. Let me skip this. If you have questions, you ask me later. So I told you, this is what I had promised you. I talked about the first 4 points. So last point, I ran out of time. Thank you very much for your kind attention and the questions. I'm happy to answer.
Questions, the floor is open for more questions. No, I need this mic.
Mandar, yeah, great talk. So, with this technical question, I think you mentioned that you determine the angle from transport. So, my question is how? And then the related question is if you have like non-uniformity,
Yeah.
can you also get some handle from that same?
Yeah. Okay. So thanks for asking this question. I will explain. Let's see. I will explain some bit of it, and some more I will explain later. Okay. So first question: how do I know from transport the angle? Right. That's a very good question. So this. This axis is density. Remember the situation is that I have flat bands, maybe in this pilot 2 overlapping set of flat bands. So I know that when I go from here to here, I fill it up completely. Okay. So and I know how much density is required to fill it up. Okay, so from there, I can have an idea of what is the unit cell, and the unit cell gives me what is the superlattice lattice constant, and that is related to the twist angle.
Because you know the band structure very well.
Yeah, here you don't you even need to know the band structure per se. It's just the symmetry. You have 4-fold degeneracy, spin 2, valley 2, and that's it. You have a band which is full. That's the only thing. We know the band structure for sure, but details of the band structure are not even needed. You have a flat band, you just get filled or empty. That's it.
You just need a gap above that band. That's all. Okay.
So the band structure is not needed. Details of the band structure are not needed. It's just each atom is of the superlattice is going to contribute some density. So that's all. It's number counting. Okay, that's answer. So let me answer your second question. How do I know the twist angle? So ideally, the way to know twist angle disorder, this is the terminology, is by imaging using STM or a technique called piezo response force microscopy. But in these devices which are sandwiched, we don't have access to the inside. But what we have access to is this, is called the moiré peak. And so if I plot it through the middle as in the dashed rectangle, I plot the resistance, I will see a moiré peak like this. Okay. If there is a twist angle disorder in your device, what happens is you have 2 different regions which have different angle. What they end up doing is giving you some structure in this. Okay. From there, you can infer. This is a limitation of this transport measurement technique. We don't exactly know what all distributions are there, but we are sure that there is a distribution of this angle disorder, and you can infer the magnitude of the angle disorder. Yeah. Does that answer the question?
Yeah.
Okay. You have a question, Kalu?
This dipole sciences that you are talking about, is it some specific geometry that you have used that leads to this?
No, good question. Thank you for asking that question because it leads me to show you. So all kinds of topological transitions. So this is not a creature, some weird anomaly of moiré system that this gives rise to. So people, even before our work, did theoretical calculation that if you look at a completely entire 3D material which undergoes a topological transition from a trivial insulator to a topological insulator, they calculated the Berry curvature dipole in some strain as a function of pressure. That also undergoes a large change at the topological transition. So this physics is general. It doesn't care about whether you are talking about moiré or not. The Berry curvature dipole is a, I would say at this point, a little explored quantity which will show signature of the topological transition in all systems. Okay, I don't have a mathematical proof for it, but what evidence that we have and our collaborators have sort of thought about is that it will undergo a change, a dramatic change across the topological transition.
When something like band inversion related.
Yeah, exactly. I mean, it's connected to this idea of band inversion. You know, when you have a topological transition in the picture that I showed you, there's a band touching, okay, which flips the sign of the Berry curvature, and that also automatically gets reflected in the Berry curvature dipole. So, you know, as a function of the electric field, what has happened here is when these are on either sides of the topological transition, the flat band touches the remote bands. It exchanges the Berry curvature, and the Chern number changes, the Berry curvature changes, the Berry curvature dipole also changes. So it's very general idea. Yes. What is important is that the symmetry has to be broken. If the system is completely symmetric, the Berry curvature dipole distribution will first moment will add up to 0. If you have electric field or some distortion in the lattice, it will show up.
Yeah, in your earlier slide, you mentioned that for this topological phase to be observed in the system, the time invariant symmetry should be broken.
If you want a non-zero Chern number, you can also have topologically non-trivial states where the one valley has a Chern number, let's say plus C. The other valley, if you don't break time reversal symmetry, you will have another other valley having a minus C Chern number. So the total Chern number is still 0, but it's topologically still non-trivial. So that's what the case is here. One valley and the other valley have opposite Chern numbers, but they still can undergo a topological transition.
So, Mandar, two related questions. One is how much strain or how much of the symmetry rating do you need in your sample to have a perceptible?
Yeah, so yeah, that's a good question. And you have a second question?
Yeah, and the second question was more, I don't know the answer, but curious, if you look at the second moment of the Berry curvature, whether that does, because that's not related to even in a symmetric situation, you would have something. I don't know if it's related to something.
Yeah, okay. So let me order the opposite order. So the higher moments also reflect the change in the topology of the system, and there is a lot of interest. And we are also trying to understand that physics ourselves, and happy to discuss more. So there are some third order also people have calculated, and I think they are all interesting. The question is how to convincingly prove that what you're measuring is meaningful. Okay. All right. So now the first question is what is the magnitude of the strain? Okay, so from our this inference from the experimental data, I think maybe I think some confirmation. We see some strain which is less than 1%, maybe 0.5 or 0.2%. Maybe I'm blacking out on the number. Maybe so. Why did you think it? 0.1. So it's very small amount of strain. You don't need a whole lot to break that symmetry. So Amit's group did lots of calculations whether some idiosyncrasy of the magnitude of the strain. So the magnitude of the Berry curvature dipole scales with the strain, but the physics is still robust. So it's actually a relatively small strain. And my contention is that almost all devices that people measure across the world, they have some bit of strain in the moiré because it's impossible to get over a micron square or 2 micron square a uniform crystal standard. which is the angle
And
disorder.
this is strain in the twist angle.
Yes, yes, it's a twist angle disorder, not the disorder of other kind.
Can I ask a question?
Yeah.
Yeah, so, what is beyond graphene? In the sense that you have these bilayer graphenes which are beautiful band structures, and now you're starting to get these brilliant moves which are because of the two layers coming together. But is it only sort of applicable to graphene-like systems, or to other interesting systems where it,
So, very good question. So the short answer to your question is this physics, as I answered one question that Kalu asked, this physics is there in conventional 3D materials also. Okay. Now, why is graphene interesting? Or are we looking at physics which is this kind of some unicorn-like physics which is this graphene world? No. What is nice about the 2D materials is the devices, the kind of knob control that I have, independent control. I can control density, I can control electric field. That knob simply doesn't exist in the 3D materials and conventional materials. Okay, so it's a kind of an exploration that we use this, if you use kind of a toy system which you can control parameters with utmost precision. You understand the underlying physics, then you go back and look at other materials which I would call conventional materials. I don't have doubt that this physics is pervasive, in the sense it's very general. Okay, so the power of these 2D twisted systems is there. It's a laboratory for kind of exploring. Okay, there is superconductivity, which is, for example, if these two layers which are twisted by this angle, that fundamental understanding. I mean, maybe twisted layers of bilayers of graphene may not be useful for anything in terms of practical, but how the superconductivity arises could shed light on something different. But that is the power.
There is no relationship to the underlying band structure of that material. Is it? In the sense, graphene has a very specific band structure, right? Not every material has that kind of.
Yeah, but when you distill it to this point, it basically just becomes. I mean, there is a symmetrical challenge, but it becomes a flat band.
Okay.
Okay, so it's, in a way, it's a knob to tune this bandwidth with respect to Coulombic interaction. I mean, I'm kind of simplifying it, but not just graphene, people have shown in cousins of graphene, which are two-dimensional, which are semiconductors, where also you see superconductivity, you see correlated states. So it's something more universal that you're controlling some essential band property. So from there, if you can connect to your understanding of conventional, let's say, correlated materials, then I would say you would have gained some insight about understanding, because in many of the conventional correlated materials, microscopic mechanism is not fully understood.
Right. So, but then the point is that you have sort of van der Waals solids or these low dimensional, but you have a control to understand these topological transformations.
Yes, the kind of control you have with these devices and these materials, you do not have yet with other 3D materials. Okay. You use these to leapfrog into conventional materials if you like.
Okay, great. Thank you, Mandar. On that note, we will end this wonderful solution. Zoom audience, do you have any question? I'm sorry, I forgot to ask that.
Yeah, I have two questions. May I ask?
Yes, please.
Yeah.
Sorry.
Hi Mandar, this is nice talk. I am Shurajit. I have a one question. That is that on a correlated system, you have an influence on a like superconductivity magnetism have an influence on how you align your sample with the hexagonal boron nitride. Does this Berry curvature has the same, this physics has the same influence?
Sorry, your question was longish. Can you repeat once the question?
Yeah. So people has find that like Eva Andari groups and other groups that if your graphene is aligned with HBN, then you might lose the superconductivity and the ferromagnetism appeared, and other correlated insulator may miss. So my question is, do you have the same influence? Because HBN and this graphene also create the moiré superlattice. So this is the first evidence one got from STM.
So that is one additional knob for tuning the band structure. So today in my talk, I did not talk about alignment with HPN. That's another moiré that you can get. That controls, it actually breaks another symmetry, which is the sublattice symmetry. When you align HPN to graphene, you basically lift the symmetry between two sublattices of, let's say, graphene family that you started with. So it's another norm. So if you twist HBN at large angles, then that moiré is lost. So for example, 30 degrees. So we most of our devices are at large angles, but people use that alignment also to control the property that they, for example, the magnetism, the anomalous, quantum anomalous Hall effect experiments that people have done. They basically align graphene to let's say one HPN layer, either the bottom or the top.
And so that alignment has no influence on this Berry curvature physics.
It will modify the band structure, but it won't radically change any of this.
Okay. Another question is that parametric plot that you have shown that this nonlinear Hall, this first moment of Berry curvature, that what is the frequency range that is up to work that you measure, let's say.
So these are relatively low frequency experiments at frequencies up to, I think, something like maybe order of 100 hertz.
Does it break that if you do this measurement with as a function of frequency, as anywhere does it break, because its relation shows that independent of frequency, it isn't it?
Yeah, so it is the frequency, the physics is independent of frequency, but experimentally, as you know, if you have a lot of filtered lines inside your cryostat, then the lines have frequency response, which you don't want to go near the cutoff of the lines. Often, at least in our dilution phase, we have significant amount of filtering to reduce high frequency noise coming down to the mixing chamber plate. So we don't, I mean, we haven't scanned the frequency, but the range that is available to us over which we did it is something like order of 100 hertz or maybe 200 hertz. I don't remember exactly, but it's
okay.
It's even hard to take the measurement and you vary the frequency in low range within 200 hertz.
So it's about 200 hertz window, but the cutoff of lines and capacitive coupling can start to happen at kilohertz in most of the cryostat wiring.
Right. The last question to be finished with, that it is a basic question that you have talked about this picking up this Berry curvature by these electrons. Does this point that around which this wave function is wrapping, is that has to be happened that around this band of singularity, or it could have been any point?
So it has nothing to do with Van Hoff's singularity. I mean, Berry curvature lives at the band edges. That's where it's strongest. Away from the bands, in the middle of the band, the Berry curvature dies. I mean, the magnitude becomes very small. That's.
I have a doubt that it is around with the Dirac cone points or not. This is momentum state.
Graphene, there is no Berry curvature. You have to break the sublattice symmetry to get Berry curvature in
okay.
Okay.
Thanks, Mandar. Yeah.
For asking those questions, and I would like to conclude the colloquium now and thank once again Mandar for this wonderful presentation and introducing to some new physics in these bilayer reference systems. So thank you, Mandar. And I would like to thank also the AD staff here for arranging for everything within the 86 letter theater. So thank you, Mr. Candidates. And next week, I don't know if people have cleared up, but next week we will have 2022 Abel Prize in Mathematics Colloquium. So we have 3 speakers from in-house TIFR, and please do join in physically in this auditorium. Thank you.
Yeah, great, thanks.
Thanks, Mandar. Thank you. It was very nice. So
Thanks.
We'll have some tea.
Okay,
sure. Umesh, good. Your work was great.
Somewhere in the talk you said that when you apply perpendicular electric field, you open up a gap in twisted bilayer graphing as well.
In bilayer,
Bilayer, I don't think.
no, in simple bilayer graphing, you open up a gap.
Simple bilayer.
Yeah, and twisted, no, twisted bilayer, no, twisted double bilayer.
Yes.
Yeah, I may have misspoken at that instance, but not in twisted, not in twisted bilayer, but in twisted double bilayer.
Yes.
Sorry.
Yeah, go ahead.
So, another to the solid lattice, we can have an optical lattice.
Yeah.
Where we can have the arrangement of the reflective
Yes.
lattice, right? So, can we see if we, let's say, we got the inverse material, can we see?
People already see that. Already physics of, you have to talk about somewhat analogous language, but it's the same. People have made this one-dimensional edge mode circulating. People are already made with optical lattices.
But how would you make this time inverse symmetry?
Time reversal symmetry. I'm not an expert at optics, but I don't know the answer to that question. How the optics people do it. You'll have, but there are lots of papers. You can look at. People have even made twisted optical superlattices. You make it on one dielectric and you make another on dielectric and you lap them together.
So why it's so interesting to see on the solid? I mean, it's much difficult to control here. And
of course, I mean, the knobs that you have here are not, I don't think will be there in optics. For example, tunable band structure means that it's like changing the lattice in situ that you can do in optics.
but I can have generate also. I mean, I can put.
You can, similarly in solids, you can make lots of devices, but that's not the same. You know, sometimes there's a physics of disorder. So the advantage with this strategy is that you don't have to worry about the physics of disorder.
बरोबर. हाँ हाँ यार थोड़ी समझे ऊपर है एकदम आप क्या हो क्या काम